So since this is my Pi Day video, I figured that the most appropriate thing we could be looking at is a picture of pi. My topic is irrational numbers. In mathematics and irrational numbers, any real number that cannot be expressed as a ratio, a over b, where a and b are integers and b is non-zero. This means that an irrational number cannot be represented as a simple fraction. Irrational numbers are those real numbers that cannot be represented as terminating or repeating decimals. As a consequence of Cantor's proof that the real numbers are uncountable and the rationals countable, it follows that almost all real numbers are irrational. When the ratio of lengths of two line segments is rational, the line segments are also described as being incommensurable, meaning that they share no common measure. Perhaps the best known irrational numbers are the ratio of a circle's circumference to its diameter, pi, Euler's number, the golden ratio, and the square root of 2. It has been suggested that the concept of irrationality was accepted by Indian mathematicians since the 7th century. The first proof of the existence of irrational numbers is usually attributed to Pythagorean, who probably discovered them while identifying sides of the pentagram. The then current Pythagorean method would have claimed that there must be some sufficiently small, indivisible unit that could fit evenly into one of these lengths as well as the other. However, Hippasus in the 5th century BC was able to deduce that there was, in fact, no common unit of measure, and that there was the assertion of such an existence was in fact a contradiction. He did this by demonstrating that if the hypotenuse of an isosceles triangle was indeed commensurable with a leg, then that the unit of measure must be both odd and even, which is impossible. His reasoning is this. Start with an isosceles right triangle, with side lengths of integers, a, b, and c. The ratio of the hypotenuse to a leg is represented by c:b. Assume a, b, and c are in the smallest possible terms. They have no common factors. By the Pythagorean theorem, c squared equals a squared plus b squared equals b squared plus b squared equals 2b, since the triangle is isosceles, a equals b. Since c squared equals 2b squared, c squared is divisible by 2 and therefore even. Since c squared is even, c must be even. And since c and b have no common factors, and c is even, b must be odd. If b were even, b and c would have a common factor of 2. Since c is even, dividing c by 2 yields an integer. Let y be this integer. C equals 2y. By squaring both sides of c equals 2y, yields c squared equals 2y squared, or c squared equals 4y squared. Substituting 4y squared for c squared in the first equation, c squared plus c squared equals 2b squared gives us 4y squared equals 2b squared. Dividing by 2 yields 2y squared equals b squared. Since y is an integer and 2y squared equals b squared is divisible by 2 and therefore even. Since b squared is even, b must be even. However, we already have asserted that b must be odd, and b cannot be both odd and even. This contradiction proves that c and b cannot both be integers, and thus the existence of a number that cannot be expressed as a ratio of two integers. This is my Pi Day video. I hope you enjoyed. Maybe some of it is a little hard to understand, but I think you can get it. Thanks. Bye.